Okay, good. Hi, that's very loud. I'm going to describe some work we've been doing to make x86 HVM more secure. So probably the biggest attack surface for an x86 HVM guest, even bigger than the hypervisor, is that presented by the QEMU device model. This is an emulated PC, complete with hard disk and network, and video controllers and so on. So I've got a diagram here about that. Each of these devices you can see here is implemented by emulation code in QEMU. And in the usual configuration, QEMU runs as a process in DOM0 with complete privilege. Any vulnerability in the QEMU device model is a vulnerability in the whole Zen system, which can allow the guest to probably take over the host. Now we have a number of strategies to deal with this kind of problem. The most obvious one is don't use HVM. HVM is not only less secure, it's also much more complicated. So if you can, use PV or PVH, and then QEMU just disappears, at least as the system emulation part does, and so you don't need to concern yourself with this. If you must use HVM, then you have the option of using a QEMU stub domain. Not that diagram yet. Let's have that one. A QEMU stub domain. So some Zen project downstreams are using QEMU stub domains to quite good effect. This can be quite complex to set up. The upstream offering is based on an ancient version of QEMU compiled in a strange way against Minios. And well, you don't really care very much that it's from a security point of view, that it's an ancient version of QEMU that you can't really security patch because it runs inside the guest context, so its security problems aren't an issue. But it does have bugs, and its kind of feature set is rather limited, and the build testing system is horrific. Some people have got Linux-based stub domains. That's very cool, but they're not really upstream support for that. It's not very good in QEMU and in Zen, and it's not really deployable if you're using like a distro setup or something. So we're working on that, but it's not here yet. Most of our HVM user base, that's not a very good option. It has some slight scalability problems because you need now 2 domains for every guest as well. So those users need something to help mitigate QEMU bugs. And that is what I'm talking about today. We're basically aiming to provide defense in depth here. We're rearranging the security boundary to go outside QEMU so that QEMU is no longer trusted. It's basically the same code running in basically the same way with the same vulnerabilities on its attack surface to the guest, but we are aiming to mitigate the risk by stopping QEMU from being able to do bad things to the host. Don't know if that's clear on this diagram, but it gives you a substantially narrower security boundary rather than a number of complicated emulated devices. QEMU's interfaces to the rest of the system are limited to some talking to libxl, a little bit of talking to the DOM0 kernel. Those interfaces themselves have been shrunk somewhat as part of this work. So where are we with this? Well, we have done quite a bit of work. It's quite good, really. It works reasonably well. It's tested. So in Zen 4.12, this new deprivileged mode is in tech preview status, but normally that wouldn't give you any kind of security support. So if you turned it on, you'd be on your own. But we are confident enough that this doesn't make anything worse, that we're offering this special security statement. So although we're not quite confident that it will deliver all of the security benefits that I'm kind of advertising, and the next slide will explain maybe why that's the case. We are relatively confident that it doesn't make anything worse. So we will, if we find any bug where this makes things worse, we'll certainly issue an advisory. And in practice, actually, the things that we've done so far mean that things are better than it would appear just from this slide. And much of the time, an attacker who gains control of QEMU will be able to do much less damage with this feature enabled than without. Mostly limited denial of service attacks. Right, I'm not going to test you on this later. This is a list of all of the things that we have, kind of like our to-do list for the QEMU deprivilege. Each of these things on the left-hand column is a problem that most of these are capabilities that QEMU has to do some bad thing. And then we've got a solution in each case, hopefully, and the status column that tells you where we are with that. So this is quite a substantial project. Some of these rows are a lot bigger than others. There's a lot of this here. And the reason there's a lot of this here is because QEMU did have complete access to the Linux syscall API as root. And we've been kind of chopping that down, reducing, eliminating the accesses it doesn't need, and doing more complicated things, the accesses where it does still need some kind of ability to do something. So I'm going to zoom in on one of these, just to give a flavor of what we've done. So there's going to be the Hypercalls one, which is on the top of the list there. So a QEMU device model needs to make hypercalls related to its guest. It needs to be able to deliver interrupts, adjust the domain's physical memory map, declare that the guest has crashed, various kind of things. Those things shouldn't affect other guests on the system, but it definitely needs to have pretty much full control of the guest it's managing because it's emulating the PC that the guest is running on, not the actual CPU, which is run, the code runs on the real CPU, but all the peripherals, and it needs to be able to emulate those. So previously, QEMU could make these hypercalls just because it was a privileged process in DOM0, and so it had complete privilege to make any hypercall it liked. So we had to strip it of this privilege. And so we've had to make a distinction in DOM0 between this QEMU process, which has only this restricted privilege, and other processes on DOM0 that have full privilege. And that distinction has to be enforced by the kernel driver that is used by processes in DOM0 to make hypercalls. So that kernel driver is the same kernel driver with a deprivileged QEMU, but it has a new feature enabled where during QEMU startup, it makes a special, before it starts to interact with the guest and might be taken over while it's still trusted, it makes a special ioctl to the driver to say, I'm going to be the QEMU for this particular domain. And after that, the priv command driver restricts the hypercalls that QEMU can make. So, this is all very well, but the actual set of hypercalls that QEMU needs to make is very open-ended, and they don't have a stable, there's not really a stable list of them. They come and go with different Zen versions. And tracking that in the Linux kernel, having a table in the Linux kernel which listed all of the hypercalls that was like a kind of, I don't know, you could have had like a firewall rule thing that listed all the hypercalls, that would be completely unmanageable because you'd have to keep the list in Linux and the list in Zen up to date, and if they got out of sync, it would be a security bug or things wouldn't work. So instead, we invented a completely new meta hypercall called DMOP. It stands for device model operation. The DMOP hypercall has a part that's in a standard form. So you can see here, this is the actual arguments of the hypercall, and it's got a DOM ID, that's the target DOM ID, and this pile of buffers. The target hypercall can be checked because it's always in the same place in the arguments. The priv command driver, when it's running in this restricted mode, can check that that DOM ID is the expected domain. And we've got these buffers. The reason we've got the buffers laid out like this is because hypercalls are made, they typically have arguments that are provided in memory, and Zen will just read or write the hypercall arguments and return values to those addresses. And we need to stop the QEMU from telling Zen via these hypercall parameters to read memory that QEMU shouldn't have access to, or to write memory that it shouldn't have access to. So all of those kind of indirect arguments are in these buffers now. And you can see there's just a table of buffers, length, each one is a length and an address. And the priv command driver can check that all of those addresses correspond to the QEMU's legit address space. The green parts are the actual details, complicated stuff to do with domain management, and the Linux kernel doesn't need to consider that at all. It can trust that Zen will only allow accesses to these memory regions and only for that domain, and the rest is up to Zen to enforce. So this is quite complicated. This is one of the more complicated extra pieces of code we've had to do. There's been a lot of other kind of shuffling around. If we go back to that list, for example, XenStore is on this list as well. QEMU did do a lot of stuff talking to the tool stack via XenStore. We did have a previous idea of how to do XenStore, but actually when we looked at the code again, most of those uses of XenStore could be removed from QEMU, and now we do that communication mostly via QMP. And you can see that QMP is also blocking QMP blocks libxl. That's a to-do list item. We're working on that, right? And that's necessary anyway because before we started this work, QEMU and libxl were communicating both over XenStore and via QMP, and the QMP parts couldn't be really got rid of. Now, if we look at this list, the ones that are left as not completely done, we've got a bit of testing left to do. We've got some basically denial of service type problems left, where QEMU can use too many system resources, it might be able to block the tool stack, but most of the abilities of QEMU to access arbitrary host resources, access arbitrary memory have been removed. So that's why I'm saying that probably you're not likely to suffer worse than a denial of service. But in order to declare this properly fully supported, we've got to finish these. Many of them are fairly straightforward, and we need to actually get them tested. We do have some test code for some of these that are listed as not tested. We've got kind of work in progress test code. So I'm hoping this will happen maybe in the next few months. We'll see how that goes. We can be optimistic, can't we? So the question is, when should you enable this feature? It's difficult to quantify this. The benefit is a reduced security risk. You will hopefully find that maybe if there's a security advisory affecting QEMU, you could put off the update or maybe not update it at all. And certainly the update may be less urgent for you. But if we go back to this list, there are some reasons why maybe you don't want to enable this, and the worst of these is that there are some features that currently don't work at all. The most obvious annoying one of these is CD-ROM insert. We have done most of the work to make that work, but it's not quite there, and currently if you try that, you just get errors. The QDisk backends, which are used in upstream Zen to support QCOW2 and other kinds of interesting image formats, are also not supported because we need to be able to separate the code out to talk to two. They're going to have to be two instances of QEMU, one of which only runs QDisk backends, and one of which runs all the kind of really vulnerable PC emulation. And we have some ancient patches to do that, but it's quite involved. That'll be a while, I think. I don't think that's a blocker for making this supported. We'll just, to make this supported, we'll just say, you know, that configuration doesn't work, and we'll just document that. There are probably some other bugs and limitations. We don't know exactly what they are. We do have it tested in OSS test. We don't think it's been widely deployed yet, so it depends how novel you are. Also, there's a bit of a kind of wrinkle in the deployment. It likes to have a UID per domain, per DOM ID, so you need to wrestle your system configuration a bit for that. Okay, so that's mostly what I had prepared to say. This is my references slide. So firstly, I should say thank you to all the, we've had a lot of people involved in this. I went through the logs of all various projects to find who had, you know, whose commits had touched the relevant code. I may very well have missed somebody. I may have missed an entire tree somewhere, but you can see it's been very much a joint effort. It's quite easy to turn it on. You just stick dm restrict equals 1 in your libxl configuration file. And the documentation in tree is reasonably up to date. So I think that means I should take questions. Yes, Paul. So the question is, QEMU now has the ability to be instructed to create PV backends, QDisk PV backends via QMP. And the question is, given that, would it be reasonable to try to do that in the restricted QEMU? And I think the answer, to have only one QEMU instance that. Could you use the mic? Then I won't have to repeat and mangle your question.
Yeah, okay, it's on. Yeah, so potentially we could have a single QEMU instance to act as PV backend for all guests, because there's IO thread support in there as well, so it's not like you're going to be serializing every guest against every other guest as far as PV access is concerned. So
that's an interesting idea. I haven't thought of that at all.
So that way we don't have to have two instances of QEMU per guest.
Right, and you don't have to manage the startup and shutdown of
exactly. You just have one that starts at that host.
I don't know how good QEMU's error handling is on the PV.
Since I fixed it, it's not bad.
Oh well. Okay, so maybe we should do that then.
I think that would be easier than potentially having to teach the tool stack to spawn two instances and manage
those. It's not
those.
just the network and disk backends though, where there's also potentially the VNC server, PV USB, PD every random thing that...
Well, I mean, yeah, this is part of the sort of ongoing work I think needs to be done to move over to the new backend framework that I added. I think if we start to port these things across, then it becomes feasible for all PV backends essentially that we use QEMU for. Well, it depends how much mapping, unmapping we do. Let me see.
I mean, if you run all the packets from a single process, every time you map and unmap, it takes a lot.
Yeah, but that's the point. They're not. They're running in separate threads. If you use I/O threads in QEMU, then you can have them on separate threads. Yeah. Well, so no, they don't have to.
They
they're
share
not,
a single
there's a
address
shared
space.
address space, but they can be scheduled simultaneously.
Yeah, but I mean, map and unmap is something that somebody is kernel and need to take the process.
Okay, well, yeah, that's true. I mean, we don't use map and unmap in the storage backend. We use copy instead. Yes, other backends may not be so fortunate.
I think that, I mean, if I go back to my list of my to-do list, I think the QDIS thing, I mean, we've got some other work to do while we think about what the best way to organize this is.
And I think the right answer for Pastor is just let's take it out.
Right. I mean, I've got like TBD here, and the answer is like, somebody who wants to make that work can come and try and fix it. I think it's quite hard.
Well, this is what Roger's talking about, right?
I think we had some more questions, maybe.
So I'll start. 2 questions. So first one is, once you get all the FD passing, unshare the net or the mount namespace, right?
I think that's. That's interesting. It's not on our list.
We talked about it in Nanjing. I just remember.
Right. There is. If I go to this document, Docs Designs QEMU Deprivileged, does that mention unsharing the mount namespace? If it doesn't, please send a patch to it.
Okay.
Thank you.
And then the second one, UIDs. So what UIDs are you using?
So the current approach is there's a kind of, you can control how it does it. The second setup that I would recommend is you create a base user. So it's like a dummy user that you create, and it will use, this is controlled by code in libxl, it will use that UID and 2 to the 16 UIDs onwards from it. So whatever value you give that user, it will use that block of UIDs, and that's how you control that. Yeah, so it combines that base user and basically just adds the DOM ID to it, and then it uses that UID. And it's got some mechanism to, when the DOM ID is reused, to make sure that there's no leftover processes from the old UID.
So uint has worked poorly for Android, right? Separating out that they toss that in the river. So why don't we use some of the more modern things like user namespaces and just keep it as the same PID inside of a user namespace?
I don't know what you're talking about for Android. I think the current approach will work well. I would have expected it to.
So like Android design used to be, like their security model used to be, we'll just make for every app, it'll have its own UID, right? And so now they're, I don't know, I'm not an Android developer, somebody here, but they've switched into like namespacing and separating out. So just because that model kept getting broken.
Okay, I don't know anything about that. How did it get broken?
I mean, you're in the same namespace, users attack users and badness. Boogeyman, scary things.
Let's talk about that offline.
Okay, fair enough.
Anyone else? I thought there was one other question that I saw, but I can't remember where it was. No? So I'm not relying, I mean, to answer your question a bit more about UIDs, I don't think we're relying completely on UIDs, right? So we want to unshare, if you look at the list, right, we're intending to unshare various namespaces, and you're right about the mount namespace. I don't think it's necessary to unshare the UID namespace as well, and unsharing the UID namespace has some performance implications because it adds another layer of indirection in the kernel. And given that there will be no other processes with this UID,
How many syscalls and everything is that QEMU truly making?
quite a lot. Yeah, I mean, every time it needs to map some guest memory, it's making map calls on brief command. Okay, well, I think, oh, yeah.
My question is if the changes you did are in common code and not x86. The reason I'm asking is I'm looking for enabling with I/O, and in that case, I would probably use QEMU to emulate some of the devices on ARM.
So that's a good question. I think DMOP is not x86 specific. So yes, this is all applicable. If you were to try and create an I/O server, right? I mean, I think in fact you can see that. Let me see if I can find that on Zen DMOP create I/O rec server, right? I think that DMOP is platform independent.
Then ARM, this is some like
Right.
work in progress.
I mean, I don't think it's implemented on ARM, but there's no reason why you couldn't implement it on ARM, and then all of this that I've described here on this slide would be totally applicable. You probably have to do some tool stack work, because right now in libxl doesn't expect, to do any of this QEMU device model stuff other than x86 HVM.
Okay, thank you.
Okay, thank you very much.